Apache Spark is a distributed processing engine designed to handle large-scale data in parallel. It has become a powerful tool for big data analytics, enabling organizations to process and analyze massive data sets efficiently. At a high level, a Spark application has three major parts. The first part is the driver, which acts as the central control unit of the application. It is responsible for creating the execution plan and managing the overall workflow. The driver is like the brain of the application, making decisions on how tasks should be executed and coordinating with other components. The second part is the cluster manager, which plays a crucial role in allocating resources across the cluster. It manages the availability of computing resources and ensures that each task gets the necessary power to run smoothly. This component helps optimize resource usage and prevent overloading any single node. The third part consists of the executors, which run on worker nodes and perform the actual data processing. These are the workers that carry out the tasks assigned by the driver. Each executor uses the CPU and memory available on its node to process data partitions in parallel. This parallel processing capability is one of the key reasons why Spark is fast and scalable. By dividing data into smaller chunks and processing them simultaneously, Spark can handle complex computations much more efficiently than traditional systems. The driver builds the execution plan, sends work to executors, and collects results. It communicates with the cluster manager to request resources and then distributes tasks to the executors. Once the executors complete their tasks, the driver gathers the results and provides a final output. This collaborative approach ensures that the entire system works in harmony, delivering high performance and reliability. Executors use CPU and memory to process data partitions in parallel, making Spark fast and scalable. This architecture allows Spark to efficiently manage large volumes of data while maintaining speed and responsiveness. Whether it's batch processing, stream processing, or machine learning tasks, Spark's design makes it a versatile and powerful solution for modern data challenges. When you submit a Spark application, the driver program starts first. This is the main process that initiates and controls the entire execution flow of your application. The driver's primary role is to create a Spark session, which serves as the entry point for interacting with Spark's functionalities. Once the session is established, it analyzes your code, breaking it down into logical operations and building an execution plan that outlines how the tasks will be carried out. After this, the driver communicates with the cluster manager to request the necessary resources. The cluster manager is responsible for managing the allocation of computing resources across the cluster. It does not perform any data processing itself, but instead ensures that the required executors are launched on available worker nodes. These executors are the actual processes that execute the tasks assigned by the driver. Each executor comes equipped with a certain number of CPU cores, memory, and task slots, allowing it to handle multiple tasks simultaneously. As the job runs, the driver continues to oversee the progress, coordinating the distribution of work among the executors. In return, the executors send back regular updates on their status and the results of the tasks they complete. In essence, the driver acts as the central controller of the Spark application, while the executors focus on carrying out the distributed computations efficiently. This division of responsibilities ensures that the application runs smoothly and scales effectively across the cluster. Spark doesn't run every line of code right away. Instead, it builds a logical plan of operations and waits for a specific action to trigger the actual computation. Most operations, like filter or select, are lazy transformations. These operations don't execute immediately, they just define what needs to be done. Spark waits until you do an action, like count, collect, or write. At that point, Spark creates a job. This job is a sequence of steps that need to be completed to produce the final result. A job gets split into stages, and each stage gets split into tasks. Stages are separated by shuffle boundaries, which happen when data needs to move across the cluster, like after a group by or join. This movement of data is necessary to reorganize it for further processing. Tasks are the smallest units of work, and they run on executors. Executors are the workers that perform the actual computation. In real use, Spark turns your code into many parallel tasks that process different parts of the data. This approach allows for efficient use of resources and helps handle large data sets effectively. By breaking down the work into smaller pieces, Spark can distribute the processing across multiple nodes in a cluster, making it faster and more scalable. A core Spark idea is the DAG, which stands for Directed Acyclic Graph. This concept is fundamental to how Spark processes data efficiently and in a structured way. The graph represents the sequence of transformations and the dependencies between them, making it easier to understand how each step connects to the next. It is called directed because the steps have a clear order, meaning that one operation must be completed before the next can begin. And it is acyclic because the flow moves forward without loops, ensuring that no operation repeats unnecessarily. Spark uses this DAG to understand the whole pipeline before execution, allowing the driver to optimize the plan, combine operations, and reduce unnecessary work. This optimization helps improve performance and resource usage. Narrow transformations, like map or filter, usually keep processing within the same partition, which means they don't require moving data between different parts of the cluster. Wide transformations, like group by or join, often require shuffling data across the cluster and usually create a new stage. These steps are more complex and involve reorganizing data, which can impact performance and memory usage. Understanding the difference between these two types of transformations is key to writing efficient Spark applications. Partitioning is a fundamental concept in Spark that plays a crucial role in how data is processed and managed across a cluster. When Spark reads a dataset, it automatically splits the data into smaller chunks called partitions. These partitions are then spread out across different executors in the cluster, allowing each executor to work on its own portion of the data. Each partition typically corresponds to a single task in Spark, which means that the number of partitions directly affects how many tasks can be executed in parallel. This is what enables Spark to perform fast and efficient distributed computing. If you have more partitions, Spark has the potential to run more tasks simultaneously, provided there are enough CPU cores available to handle them. However, finding the right balance is essential. Having too few partitions might mean that the cluster isn't being used to its full potential, leading to underutilization of resources. On the other hand, creating too many partitions can lead to excessive overhead due to the increased number of tasks that need to be scheduled and managed. To manage this balance, Spark provides tools like repartition and coalesce. These operations allow users to adjust the number of partitions, helping to optimize data distribution and ensure that Spark can achieve the best possible level of parallelism for their specific workload. Spark performance is closely tied to the availability and efficiency of CPU and memory resources. The driver, which acts as the central coordinator for the Spark application, requires sufficient memory to manage the application's execution and store metadata about the data being processed. However, the majority of intensive computational tasks are carried out by the executors, which are the worker processes responsible for executing tasks on the cluster. Each executor is equipped with a certain number of CPU cores and a specific amount of memory. These resources determine how much work the executor can handle at any given time. Typically, a single CPU core can process one task at a time, meaning that the total number of available cores directly influences the level of parallelism in the system. More cores allow more tasks to run simultaneously, which can significantly improve processing speed. Executor memory plays an equally important role in Spark performance. It is used for execution-related operations such as joining datasets, sorting data, and performing aggregations. Additionally, Spark uses memory to store cached or persisted data, which helps avoid recomputation and speeds up repeated queries. If the memory allocated to executors is too limited, Spark may need to spill data to disk, which is much slower than in-memory operations. This can lead to increased latency and reduced overall performance. Therefore, ensuring that each executor has enough memory is crucial for maintaining efficient execution. Optimizing key parameters such as the number of executor cores, the amount of executor memory, driver memory, and the number of partitions is a fundamental part of tuning a Spark application. These settings directly impact how well the system can handle large-scale data processing and ensure that resources are used effectively. By carefully adjusting these configurations, developers can achieve better performance and more reliable results in their Spark applications. Let's bring everything together with one simple flow. Understanding how Spark operates can help you better manage and optimize your applications. It all starts when the user submits a Spark application, which is essentially a program written in Scala, Java, Python, or R. This submission triggers the entire process, setting the stage for what follows. Once the application is submitted, the driver program begins to run. The driver's main job is to create a Spark session, which acts as the entry point to interact with Spark. During this phase, the driver also builds the Directed Acyclic Graph, DAG, of the operations that need to be performed. This DAG represents the logical plan of the computation, and it's transformed into an execution plan that Spark can actually carry out. When an action is called, such as count, collect, or save as text file, Spark launches a job. Actions are what trigger the actual computation, as opposed to transformations, which are lazy and only define the operations to be performed. This job is then broken down into stages based on shuffle boundaries. Shuffles occur when data needs to be redistributed across partitions, often due to operations like group by or join. Each stage is further divided into tasks, which are the smallest units of work that can be executed by a single thread. These tasks are usually responsible for processing one partition of data. Partitions are the individual chunks of data that are processed in parallel across the cluster. The cluster manager, such as Yarn, Mesos, or Kubernetes, is responsible for allocating resources and managing the executors. Once the resources are available, the executors, worker processes running on the cluster, execute the tasks assigned to them. As each task completes, the results are sent back to the driver, which aggregates these results and returns them to the user. If you remember only one idea, remember this. Spark works by planning intelligently and executing many small tasks in parallel across distributed data. This approach allows Spark to efficiently handle large-scale data processing, making it a powerful tool for big data applications.